Okay, let's get started. So we have a lot to cover today. We're going to finish the model language part. Next week, we're moving to the program language, so we can dive into the kernel. So I guess most of you have started assignment 2. So in assignment 2, you are writing a function in assembly, and in your function, you are calling a C function. And today we first look at how we can implement a C function. So no matter what function, what language, programming language you use, eventually they compile into just a machine code, CPU instructions, right? So if you develop a C function or any other function, so you are writing code. So obviously you will have code, and that will eventually become machine instructions. Then you also have parameters for that code, for that function. So every time you call that function, every invocation of that function, you may give different parameters. That's why there is something called an actual parameter. Something is you represent in that function when you implement. Then the function may have one or more return values, and that function may use something called global variables, which means that global variable can be accessed by that function and also by other functions. Then a function may also have multiple local variables, and those local variables are only accessible by that function. They are only supposed to be accessed by that function. There could be other temp variables, not very important. Then there is also a return address. So when that function returns, it is please solve. Do you have any questions? Okay. So then there are also return address for a function. When that function returns, it's supposed to, the CPU is supposed to keep execution from some other place. Then also for C code to implement function, we also have function string pointers and previous functions string pointers. So we're going to use several examples code examples to understand how it works. So let me emphasize what is local variables. So those are variables declared inside a function or a block. So they can only be used by the statement inside that function. And global variables, they are defined outside the function. So they should be accessible to all the functions. Now we have one example. So this is a very simple C program. We have two functions here. One is called the main function. This is the entry point of what you develop. Then the main function calls another function called func. And the main function calls func and also calls printf, which is a libc function. Func also calls the libc function printf multiple times. F here stands for format string. So that's print format string. So the main function has two arguments. So the main function is not really the signature or the prototype of the main function is defined by the C library, right? It always has a format like this. It has an int argc, this means argument count. Then it has an array. So this one means this is an array, and the star here means this is a pointer. This is a pointer to a string character. Then we have an array of a pointer, pointer of strings. Yeah. So that's what it means. So actually the main function may take other parameters as well, but this example we only have two. Then when the libc function calls your main function, because it calls your C function, it's supposed to give those parameters. Okay. Then in this main function, we have two local variables. L means local here, underscore I, which is initialized to the value 10. Okay, this is a local variable initialized to value 10. This here is another local variable, and we didn't set a value for it. Then after that, we just have two printf. The printf here, first we have a format string, then we have the address of the value we're trying to print. And we are trying to print two different addresses here, because here we use %p, p means pointer, means address. And we're trying to print the address of two global variables, which are defined outside of any function. They are not in main, they are not in func. The first global variable is an array of characters, so basically a string. And the string is just a hard-coded string. We talked about this before. This hard-coded string will go to the dot data section. So this string itself goes to dot data section, but this is a global variable. So this one, the variable itself will go to also dot data section. This one goes to read-only section. So then we have another global variable, which is a pointer to a string or character, and this global variable is not initialized. Okay, but in C, anything that is global variable that is not initialized, the C will initialize them to 0. So this one will actually be 0 when you run this program. So the main function will print out the address of those two global variables, then print out the address of the two local variables. So we talked about this before. Where do they go, the local variables? Anyone remember? Where do they go? RDI. Where? RDI. RDI. No. The RDI will have the first parameter in 64-bit. So if this program is in 64-bit, this guy will go to RDI. This guy. Yeah. This is local variable. This one doesn't go to the register RDI. Okay. Anyone remember? This one those two will go to the stack. Okay. The same thing here. Func also have its own local variables. So those two will also go to stack. But this function func, how many times we can call this function? You wrote this function, how many times you can call that function? Many times what you want, right? You can call it once, you can call it twice, but many times you want. But every time you call it, it will have its own version of those two local variables. Okay. So which means when you call this function twice, those two local variables, they will have a different addresses. There should be multiple copies of them because they are local to this function.
You have a different stack every time.
Exactly. So every function at runtime, they have their own stack. Yeah. Then the main function we just call func, and we put the parameter here 10. Then we call it printf 3 times. It print out the address of two local variables. It also print out where the function is itself it is, then just a return. Yeah. So if we run this program, let's run this program on our platform. So we first run a 32-bit version of this program, and you can see here, this program only print out those several lines. So first print out where the global variable is. This is 32-bit, which means 4 GB of memory. The address should be 4 bytes. And the global variable is somewhere at 56, 58, 78, 20. This is the global variable. So remember the address is from 0 to OF, right? So this is like the bottom half of the memory. So the stack, I showed you the map last week. Where is the stack? The stack is at the top, right? So then the local variables, we have the main function, we have li and lu. The func will also have global variables, and even if they have the same name, they are actually different things. And the main functions, li is at the address ffce266. So this is a very high address, right? Because the highest address is just 8Fs. So this is a very high address. And we declare the function li first, then we declare the function lu. So the one we declare first has a higher address. This is DC, right? The stack goes down. And the second variable we have T8, has a lower address. That's because the stack goes down. Then the main function we'll call the func function. So we have main function first, then we have func. And the stack goes down, which means the local variables of func will have an even lower address of the local variables in the main, right? So the li in func have an address AC, which is 32 bytes lower than DC. Then this one is at A8. Then the P, this one is for, P is another. Oh, P is another variable here. So P is actually the parameter for the function, right? So P has an address a little bit higher than those two. So P is at C0. So P is actually between those two. So P is also on the stack. So the parameter is also on the stack. This is for the 32-bit. If we look at the 64-bit version of this, the address is just longer. This is 8 bytes. And the global variables are still somewhere in the middle of the address space. Lower half, the 4 local variables that at a much higher address, but not at the top, because the current OS and current CPU, we're not really using the full 64-bit. We're using 39-bit, I believe. So that's why this is already at the very top. Then you can see the address, they actually go down because the stack goes down. So here, it's a little bit interesting because P is actually the parameter, right? P is actually a parameter. So for 64-bit, this should go to RDI, right? If it go to RDI, it doesn't have an address. Why there is an address? That's because when we do this, the compiler made some changes to make this, move this into a stack variable. That's why there is an address. Okay. So now we say that there are many different components we need to really implement a function in C. We have code that go to the machine instructions, go to the text section, parameters. For 32-bit version, the parameters go to the stack. Well, we will see more examples. Then for 64-bit version, we use register first. If we do not have enough registers, we will also use stack. Return value go to the register EAX or RAX. Global variables go to data section or PSS section. Local variables will be on, most of them will be on stack. If we have enough registers, the compiler could choose to use registers to do that as well, because it will be much faster. Return address will be on stack. Then we also have function frame pointers. We're using the register BP or EBP or RBP to do that. Then the previous functions frame pointers will also be saved on stack. We're going to see more examples of that. So each process, we haven't talked about the concept of process yet. That's the abstraction of a running program in our OS. So each process has a stack in memory. So actually every thread of a process have their own stack. So every execution of a program, they have their own stack. And we store local variables there, we store arguments there, we store return address there. So on x86, the stack goes from higher address to lower address. Most of the machines you are using today, stack goes from higher address to lower address. We use the register RSP, ESP to point to the bottom of the stack. Well, some people will say that's the top of stack, which is the newest data in the stack. The RBP points to the base of the current function's frame. We will look at that soon. So let's say we have another example. We have a main function. Main function calls two functions, foo and bus. And we have x for foo, y for bus. That's the parameters. So this is the main function. So when you execute this function will first have its own stack, the blue part. Okay, that's that function's stack. Then the next function we're going to execute will be foo. Okay, foo. Then foo, the orange one, will also have its own stack because the stack goes from a higher address to a lower address. It will have a lower region than the blue part, which is the main function stack. Then foo calls another function bar. So bar, this function will be executed earlier than the function bus, right? Because only foo returns, we're going to execute bus. So for bar, the light blue one will be executed next. Its stack will be at a lower address than orange one. Okay. Then in bar, we also call the function bus. So that function bus actually we call it twice here. Okay. So bar will call the function bus. Then that function bus where this invocation of function bus will have its stack here, stack frame here. Now bus returns, then this part doesn't mean anything anymore. We still have data there, but we're not supposed to use it. When bar returns, this part doesn't mean anything. When foo returns, we're not using this part anymore. Then we're going to call the function bus again. So this is the first invocation of bus. This is the second invocation of bus. So the first time it's invocation, the stack is here. The second time we call that, its stack will be here actually, will be after main function. So let's look at a concrete example. Let's use the previous function as an example. So this is the assembly code, or this is actually the machine code for the global variable state code I showed you just now. The left-hand side, we have the address of this function, and you can see this address looks like very small. It's all zero, right? Because this is not the runtime address. This is an offset we're going to add at a runtime. We're going to put the whole thing at a base, and we don't know where we're going to put it right now. So we're not running this program right now. We're only looking at its code. So that's why the address looks very small. Then we have all the instructions here for this function. The very first instruction is 4 bytes. It's called NBR64. This is a security feature. We can ignore it for now. The second instruction is only 1 byte. The byte code is 55. That's a hex value of that. So the meaning of that instruction is push RBP. RBP is a register. That's a base register. RBP already has some value when we enter this function, and we are going to push it. So why do we push something? Add the stack? Okay, but why do we want to put it onto the stack? Yes, we are going to, because we're going to save the value in that register, and we're going to use that register. Okay, so we do not have enough registers here, so we cannot move it to another register. Instead, we move it to stack, okay, to memory. So we push that, we move the value in RBP onto the stack, then we're going to move RSP to RBP, okay? So this push instruction will actually change the value of RSP, right? Any push will change the value RSP or EBP points to. RSP, EBP always points to the top of the stack. So here, because we're using RBP, here we're going to move some new data into RBP. We want to save the old data. That's why we're pushing it. Then we're moving the value in RSP into RBP. Then we're doing some subtraction. We subtract some constant value from RSP. So why are we doing that? Any guess? That's a good guess, but not really, because we're not moving anything here. So the RSP already points to a very lower address, no address, right? So everything that is meaningful so far has an address higher than this, right? Then we're going to move the RSP to an even lower address, but we're not changing anything in the memory in this case. We're just pointing to a lower address. So the reason we're doing this, we are reserving space for local variables. Yes. So now RSP has a lower address. Then we're going to move EDI. In this case, EDI is same as RDI. That's the first parameter. We're going to move the value from the register to RBP minus 14. Okay. So RBP points to somewhere very high. RBP minus 14, that will be our local variable. Okay. So we're actually moving the parameter to a local variable. Then we're moving RSI, the second argument, to another local variable. And this is a main function. We have two arguments, right? That's why here we are using EDI or RDI or RSI here. So after that, let's say we have multiple call statement. So what are we calling again? Go back to our code. We are calling the printf. Print out where GI is, print out where GU is, print out those two local variables. So we have 4 function calls to printf. So let's say if we find those 2 function calls. So this is the first one. Call printf, first one. Call printf, second one. Third one. Fourth one. Okay. So those are the function calls. So for each function call, we are giving it 2 different parameters, right? So each function call, we are giving it 2 different parameters. So the first one, the first parameter, the first call, the first parameter is a string. This is hard-coded string. So we're not really giving a string to the function. We're only giving the address of the string to the function. Okay. The second one, we're also giving the address of the global variable to that function. So all other 3 function calls follow the same convention. We're just giving 2 parameters. And how do we give parameters to functions? How do we set parameters in functions? This is 64-bit. Register or stack? Registers, 64-bit. The first one goes to RDI, the second one goes to RSI, right? That's why you will see 2 more instructions here. We are using an instruction called the load effective address. So basically, we're still loading or moving some address to the register. We're loading the address, this address, to the register RSI. We're loading a different address to the register RDI. Okay. So RDI is the first argument, right? So RDI will point to the string. RSI will point to the address of the global variable. Okay. So this is how we are setting the parameters for the function call printf. So after that, we are actually making a function call printf. Okay. So the second time we call function printf, we will do the same thing. We will set RSI and RDI again. The same thing here, RDI and RSI. Make sense? So that's how it works. So if we go back to the 32-bit version, this is a 32-bit version of the same program. So in 32-bit version, we use stack. to pass parameters, not registers, because we don't have enough registers there. And we always push the parameters from the right-hand side to the left-hand side. And so we have two parameters, right? One is the global variables address, another is the strings address. So the first function call here, this one is calling the printf. We have 1, 2, 3, 4 of those. 4 calls to printf. For each function call, we are going to pass 2 parameters to it. So we need to do 2 pushes. So the first push here is push a hard-coded value. Here we have another push to a hard-coded value. So those 2 hard-coded values, one of them is the strings address, another one is the global variables address. Okay. Then the second function call the same. We push 2 different values. Even though we're calling the same function, the parameters we are providing to the function are different. So here is 40, 20, here is 40, 43, right? So that's why for other two, they also have different parameters. So that is how we pass parameters in 32-bit machines. So inside each function, at the beginning, we actually look at this a little bit. Inside the function, we always do something like this. So in the main function or in the func function, we will always do something like this. We will first push RBP or EBP. Basically, we want to save the value of RBP to the stack. And the RBP, that's a base pointer. So what the value in this is actually an address. It's supposed to point to somewhere. It points to the previous function's stack frame, actually. So we're saving the previous function's stack frame to the stack. Then we are moving the current function's stack frame to RBP. And the current function stack frame at this point is at RSP because we just pushed. So RSP is changed. And we're moving that value to RBP. Then we can have our implementation of the function there. So what we had before for the previous function are 4 function calls, right? Then when we return, the function is done. We want to return to the previous place. What we do is we first move RBP to RSP, okay? So RBP has the current RBP was set at this step. This step set RBP. Then we're going to move RBP to RSP. Then we're going to pop RBP. So basically, whatever RBP points to, we're going to pop that. Then there will be another return instruction for us to return to the where we started. So there are 2 equivalent instructions introduced. I think this was introduced in the 90s. One instruction is called enter, another one is called leave. Enter takes 2 arguments. So the enter instruction is equivalent to this. Basically, 2 instructions encoded into 1. It will be a push RBP, move RSP to RBP. Then there is another subtract. So we talked about subtract. The subtract here is to reserve space for local variables. So if you do enter 24, 0, you're basically doing those 3 instructions. They're equivalent. Leave is the option, the reverse operation of enter. Leave is equivalent to move RBP to RSP, then pop RBP. After that, you will have a return. So let's go back to our code here to look at. Let's look at the func function, which is easier. In this function, we are making 3 calls to printf. And this is a 32-bit. That's why we're going to give 2 parameters to the printf. So this is 1. This is another 2 pushes before the calling printf. Another two pushes. At the start of the function, we have under BR32, security feature, doesn't matter for now. The real first instruction is push EBP, okay? Then move ESP to EBP, then subtract some value from ESP. So what we're doing here is reserving 18, which is, how big is that? 24 bytes. 24 in decimal, 18 in hex, 24 in decimal. We're reserving 24 bytes for local variables. Then we are moving A, this is hard-coded A, to EBP minus C here. Okay. So EBP, at this point, it was changed here before. Okay? We changed it here. So EBP points to the current function's stack. Then EBP minus C, what is that address? What do you think that is? EBP minus something will be something lower than the address, right? So this is a local variable, okay? So we're setting A to a local variable. If you go back to the source code, so A in decimal is 10. When we go back to the source code, we say that we have a local variable li, and it has an initialized value of 10. Yeah. It points, EBP first of all is a register, right? So it points to where the current function's stack frame is. Yeah. Yeah.
So why would
Which one we subtract from? Yes. Oh, you're talking about that one. So this one, ESP, because let me draw it this way. So the first instruction, let's say this is our stack, and this will be high address, this will be low address. Okay. So the first instruction here is push EBP, which means the value of EBP will be saved here, right? But this is a push instruction. So after this instruction, ESP will also point to here. Make sense? Okay. Then we're going to move ESP to EBP. Okay, that's a register, which means both ESP and EBP will point to here. Okay. Then we're going to subtract 24 bytes from ESP. So EBP still points to here, but ESP will point to a much lower address here. Okay. Okay, then from here, in the future, you do any push, it will be pushed to something lower than this address. So you're not going to touch this place, right? And this place will be reserved for local variables. So this region will be reserved for local variables. Okay. Then let's look at the next one. The next one we have move 10 to EBP minus C. All right. So EBP, can you guys see it here? So EBP still points to here. The EBP minus C, because this whole thing is 24 bytes, right? C is what, 12? Yeah, C is 12. So EBP minus C will be somewhere here. That's actually our local variable Li here, right? So this local variable is in this reserved area. Okay. And how do we address this local variable? We address it with EBP minus C. But the benefit of this is no matter how many times you call this function, in each implementation of this, we're going to address this as EBP minus C. But every time you call it, it has a different EBP. So even if they have a different, so the relative address of that local variable to that top of that function's stack frame is always the same. So here we're moving value 10 to this local variable. This is what we're doing. Then we subtract ESP again. Okay, we move the ESP down again. So this is a little bit weird. Why the compiler is doing that? This part seems not necessary, right? It probably is not necessary. The compiler is not very smart here. The compiler probably can merge those two instructions together to make it a little bit faster. But anyway, the optimization level we're using, it generated code like this. Then after that, we are moving that, we're loading effective address of EBP minus C to EAX. So this is different from the move instruction. So you already know how to, if this is a move instruction, look at this, you know that we're going to move the value at this memory location to register EAX, right? And the value here is 10, we already know that. But if this is not a move instruction, but load effective address instruction, we're not moving the value in the memory, we're just getting the address of this, okay? The runtime address, then we're getting the address to the register EAX. Then we're going to push EAX. So we get the address of this, which is here. This address will be pushed to the stack. So this will be the address of ARI, right? So this, since this is an address, this is a pointer, this actually points to this place. Make sense? So why we are pushing this? Yes, because we are going to call the function printf, and printf second parameter is the address of that local variable, right? That's why we're pushing. And also we have another push, but this push is hard coded. That address and that address is our string. That hard coded string, local variable I blah blah blah. Okay, make sense? So this is a 64. This is 32-bit. Then let's go back to the 64-bit. The 64-bit version of Func is a little bit smaller, and we're not having so many stack operations. The difference here is the parameters, they are from registers. They're not really from passed from stack, right? So let's say what we're doing here. Push RBP, move ISP to RBP, subtract something from ISP, the same as the 32-bit. Then we're moving EDI to RBP minus 14. And EDI is the first parameter. We're moving that to a local variable. The local variable is at RBP minus 14. And that's definitely a reserved place because here we have a bigger value. This is 32 bytes. Here is 20, RBP minus 20. Then we are moving A, also the value 10, to this local variable, RBP minus 4. So we're getting that local variable's address, use the instruction, load the effective address, the same thing. Get that address into RAX, okay? So in the 32-bit, we get that into the register EAX, then we push EAX, right? Because we want to pass that parameter. 64-bit, we don't push that RAX, we move RAX into RSI. You know, that's the second parameter. And the second parameter is not on stack, it's on RSI. So we move that value to RSI. Then we move that hard-coded string address to RDI. So after these two instructions, we finished passing the parameters. Then we just need to call this function printf. Any questions? You can do that. You definitely can do that. It's just because the compiler is not making a very smart choice here. Some registers, if you want to load them, you are supposed to push them onto the stack first to make a copy of that. Some others, there are registers you don't need to. It's not because how they are wired, it's just a convention we choose. Okay. So definitely this can be optimized here. Let's say this one, where it directly load the effective address to RDI. I think we have instructions to do that. It's also possible that there's no instruction to do that. Yeah. So we already look at this example. So for 32-bit, this is what our stack looks like. Okay. When we first time we enter a function, the very first instruction we're about to execute of that function, this is what the stack looks like. Actually, we will have the return instruction, return address there, because the call instruction will push the return address onto the stack, right? Now after that, we're going to push EBP. So we have saved the EBP here. We have local variables, and the EBP where points to the saved EBP. 64-bit, we'll have saved RBP, and the RBP points to the saved RBP. 32-bit, we also have arguments there onto the stack, 34-bit, we don't have them, we have them on registers. So that's why when you say a dereference like this, parentheses RBP or EBP, you know we are trying to get the value of the saved EBP. If it's a positive number, then positive 4 or 8, that will be the return address. Then the 8 here for 32-bit actually will be the first argument. If you say a negative number and the EBP or RBP, that means we are accessing a local variable. Let's say another example. We only have two functions here. Main function calls func. Func takes 5 parameters. Then we just add them together. That's it. So the difference here is how the parameters are passed, right? Because this function is so simple, it's much more clear how we pass the parameters. This is the main function. Eventually, main function calls func, and func takes 5 arguments, right? 1, 2, 3, 4, 5. That's why we are passing those hard-coded 5 values through stack. So we push 5 first, because 5 is the last one, last parameter. Then we push 4, push 3, push 2, and push 1. Then we just call func. So for func to access those parameters, so how should the func access those parameters? Which address it will be? Let's use EBP as a base address. So it should be a positive number or negative number there. Should be a positive number because we're going to the function func. Are those the local variables of func? Not really, right? They're not local variables of func. They're the parameters of the func. So they are at a higher address. Yes. So if we go to the func here, we're getting the parameters. We're getting EBP plus 8. Okay, that's the first argument. We move that value. So the value here is supposed to be 1 actually, right? We move that value to EBX. Then we are getting the second parameter, which has EBP plus C, which is 12. And the value here is actually 2. We move that to register EAX. We add them together. Okay? So now we added 2 numbers together, the first and second one. We still have 3 numbers to add. Then we move EBP plus 10 in hex, EBP plus 16, the third parameter, to the register EAX again. Then we add EAX to EBX. So now we already added 3 numbers, still 2 more numbers to add. That's why we load 14 in hex and 18 in hex. Okay. That's how we are passing 5 parameters onto the stack. Then in that function, we retrieve those values from the stack, move them to registers so we can compute them. So if we look at the 64-bit version, so this is 32-bit. So you think the 64-bit version will be shorter or longer? The code, just the code. Which why do you think will be shorted? Yeah, so we don't need to do this move anymore, right? They're already in registers, so we can compute them directly. So this one is actually funny. This one is not optimized. So let's see what they're doing here. The values, they are already in the registers. They are in RDI, RSI, RDX, RCX, and also R8. Okay, those values are already there. Okay, what the compiler is doing is the compiler is first moving those values to a local variable, RBP -4, RBP -8, RBP -6, right? That's a local variable. Then they're trying to load it again and eventually add them together. Okay, you see what it's doing here? But that's actually not necessary. Like you said, if we choose a different optimization level, all this will not be here. We will only have the instructions adding together. Yeah. But that's, you see, compilers do not necessarily do very smart things, and the compiler do not necessarily, the fidelity is also an issue. Sometimes your C code is doing that. The compiler will do all kinds of optimizations. When you look at assembly code, when you look at how CPU is actually executing the program, you will feel they are actually different. So actually, one of our projects going on right now is we are saying that how the optimize the code will make the attack surface bigger if you want to attack hijack a program. Okay, so then we will talk about how to write assembly, since you guys are doing homework assignment too. There are some books you can read, but I'm trying to cover the basic things here. So how do you write in assembly? And you're not going to write a lot of assembly code. Just this assignment, and you're going to also read a lot of assembly code, but not really write a lot. Especially we're reading a lot of the disassemblies. So there are code generated from C code, but you don't have those source code anymore. You are trying to understand what they're doing, and you only have the binary. So every C function, it has a signature or the prototype, like the int, main, a pair of parentheses, and also parameters inside. That is called the signature or prototype. Some book call it prototype, some book call it a signature. So when you write a function, you can think about, even though it's a assembly function, you can think about I'm running a C function. So you first need to decide what parameters my function takes, and what are the return value this function will eventually give, right? What's the type of it? So let's say we write a function to find a minimum number between A and B. So the input here are two numbers, A and B. We just use none here, 64-bit, to make sense easier. Then the return value is one of them, so it's also a none, right? Then you can just write a label here, mean. Actually, there is also a keyword procedure for you to do that, but to make sense easier, we just use a label. The label eventually becomes an address. If you want to write another function like factorial, you also think, oh, the factorial takes one integer of input, and the output is also an integer, right? So we have long x, and the return value is also long. So after that, you need to write the body of the function. It will be easier if you write some high-level pseudocode or C code first, then you translate that into assembly. So you can have a higher level understanding of what you are writing, and you also have the abstraction, the concept like variables, the concept like loop here. Because at the assembly level, you don't have those anymore. At assembly level, you only have address. The variables, they're just addresses and memory range in a memory. And those loops are just unconditional jumps, right? So you probably want to have some pseudocode like this, then try to translate them into assembly. Then you need to decide what variables you want to use. And this is very complicated. But this part, you already know this. We talked about it many times. So the registers are DI, are SI, are DX, are CX, are 8, are 9. Those 6 registers, they are used for arguments. If your function has 1 argument, it will use RDI. If it has 6 arguments, it will use all of them. If it has 8 arguments, it will use all of them. Then it will also use the stack to pass the other 2 arguments. So if your function only has 2 arguments, then those 4 registers are not really used. Okay, so there are 3 for you to use. The first 2 are for the first parent parameters. Then there is another convention. Who is supposed to save those registers? There is a concept called the core-E save, also a quarter save. So which means for core-E save the registers means your function implementation, because you implement the function, your function is called by someone, right? So this is a core-E function. If you want to use those registers, you are supposed to save them first. So when your function returns, you are supposed to make sure those registers has its original value. So how do you save them? Very simple. You just push them. Just do a push R12, then you can use it. You push R13, then you can use it. Okay. If you don't do that, then the previous function the previous function calling your function is also using the value of R12. And it has some special meaning there, right? If you do not save them, then you just override it, then that function lost its R12 value. Okay. So that's why you want to save them. So this is a convention, also quarter save. So R10, R11, if the quarter wants to maintain the value of them, the quarter is supposed to save it, which means when you develop this function, you do not need to, when you develop a function, you want to use the register R10 or R11, you can just use them freely. You don't need to push them. You don't need to save them because it's supposed to be the quarter's job to do that. Obviously, all the arguments registers is also the quarter's job to save them. So let's say now we have we want to implement this. The return value eventually will always go to RAX. So the value will to RAX. Then if we want to use a local variable, and we're not going to use stack for this, use R12 for this, then we can use R12, but we're supposed to save R12 first. We need to push that. Then at the beginning of the function, we always have the prologue. At the end of the function, we always have the epilogue. And you already saw that multiple times. The prologue is just a push RBP, push core-E save the functions and use enter. So enter is push RBP, move ESP to RBP, right? Then epilogue, you are going to do a leave, which is the corresponds to enter. Then you can also, how many pushes you have there, then how many pops you should have here. Yeah. If you push the R12, we are supposed to pop R12 here. Then at the end, there should be a return instruction. So now you have the beginning, you have the end, then you just have the body to implement whatever you want to implement. Okay, so here is one example. We're not implementing the body yet, just the prologue and epilogue. This function takes 2 arguments, 2 parameters. One is in RDI, another one is in RSI. Okay, since we're not writing the body yet, we're not really using them. Okay, so we want to use a local variable R12. We're not using stack for that. We're using a register. Then, because this is a core-E saved register, we want to use it. We have to save it. We have to push it to stack, and eventually we want to pop it. Okay. So we want to use another register R13. So we push it, we pop it. Before that, Then after that, we have enter, we have leave, and this number here is to reserve for local variables. Then we write the body there. Then we translate the body. Let's say we have this two say statement. X, we assign 5 to that. Y, we assign X times 2 plus 1 to that. And we're not using stack for those two variables. We have a lot of registers here. So X is in register R10, Y is in register RBX. So how do we write this? We assign a value to X. That's very simple. We just move 5 to R10. X is in R10. Then we're going to multiply 2 to X then plus 1. Then we move R10, which is X, to another register RDX. Then we multiply 2 and with RDX. So the reason we are, I'm not sure if we have an instruction of integer multiply with R10 directly, because historically we are using RDX for it. So that's why we're moving it to RDX. But possibly the new instruction set can allow you to do R10. So has everyone tried something like this? So in your homework, you don't have to do this, right? Yeah. Anyway, here, then we're moving it to RDX, then we multiply this, then we just add 1 this. But eventually, we're moving this to where Y is in RBX. So we move RDX to RBX. Yeah. So this may not be the optimal way to implement this. We probably can save one instruction here. Then about an if statement. So here we have two local variables, but those two local variables X and Y are not in registers. They are on stack. So X is at -8 RBP, Y is at -16 RBP, and we can say after X there is Y. Okay, there's nothing in between because there are 8 bytes, right? Then we can use the temp register R10 in this example. So we're trying to compare X and Y. Then if X is less than Y, we're going to assign 7 to Y, right? So how do we implement this? How do we implement that if and also this compare? Okay, GRE is the jump instruction. You're going to use that. But how about this compare? How do we implement that? Because JE works, JE will check the flags, right? So which instruction will set the flags? Yes, the compare instruction. So what we can do here is we first move Y, which is at this address -16 RBP, to register R10. This is a temp register we can use. So now the value is in temp register. Then we compare this temp register with X. Okay, so we have to use two instructions to do this. We have to load one value from the register, from the memory to register, then compare the value in register with a value in memory. Okay, because we don't have instructions to compare two values in memory. That instruction doesn't exist. The CPU cannot do that. That's why you have to load it to a register, then compare. Okay. So this one you cannot optimize anymore. Then after that, this instruction will set the flag register. Then we can do a compare. So if Y is greater or equal, then we will go here. Otherwise, we just move 7 to Y, and the Y is at EBP -16. Yeah. So this is how you implement. Yeah, go ahead.
In it, just X, no, Y greater than X.
So yeah, so here is greater and equal, and we are comparing. Let me see. So this one is X. Oh, yeah, this is correct. So EBP -8 RBP, this is X, okay? We're actually subtracting Y from X. So the code is doing is if X is greater all equal to y, then we are going to take this jump.
Yeah, but why,
Okay.
why we define?
Yeah, let me see. If we're taking this. Oh, this is correct. What's the question? Yes, but this is what I just talked about. The compiler may not doing something faithfully to your C code. What your C code is doing is x is less than y. The code compiler is generating is we are comparing x is greater or equal than y, then we take this. They are equivalent. They're actually the same thing. Yeah. So here, if x is less than y, we are going to do this, right? So here we're saying if x is greater or equal than y, then we're going to skip this instruction and do here, right? So then this part is the same as this part. So this part will be executed if x is less than y. So this is the correct code. Yeah.
So when you, let's say we don't take the jump and we keep going down, does it still go into the else or will it skip the else?
Here it will still go to else. That's why usually here you may also have another jump instruction. Yeah. Yeah, usually we do that. Okay, another example, x is less than y, or else y, we have 9 here. So this one is very similar. We have move. So now we're moving RBP to -16 to R10. Then we are, so this is y, and this is x. Then if greater or equal, we jump to here. So here we have for the line there. So this is exactly what you were talking about here. So we have an unconditional jump here that after we finish this branch, we just jump to that. Yeah. If we don't have that, then we will keep executing this one. Yeah. So how about a while loop? A do while loop. So in C, we have a do while loop. We can also have a while do loop. So in a do while loop, we need to execute this statement or everything in this bracket, this block, once. Okay, we execute it once, then we check this predicate. In a while do loop, I will say that later. So we're going to add increment x first, then we're going to check if x is less than 10. Okay, so if x is less than 10, if x is greater or equal to 10, then we're going to get out of this loop. But at least we're executing once for this piece of this statement. So x is at a memory location, EBP -8. X is on stack, local variable. One way to do this is we add 1 to x. We didn't even load that to the register. This instruction can do that. We directly add something. Then we compare 10 to x. So basically we are subtracting 10 from x. Then if x is less than 10, then we will jump to loop. Okay, so at least we did this addition once, right? So we will jump here. So if it's not, we keep going. So a while loop, similar, but we are checking the predicate first. Then we are going to execute this statement, which means this statement may not execute even once. So we have to do the compare first. If it's greater or equal, then we directly go to the loop down. Otherwise, we keep executing, which is the addition. Then after that, we're going to do an unconditional jump to the beginning to the check again. So this is how you implement a while do loop. Okay, next we talk about recursive functions and how they are implemented. So recursion or recursive functions is just an implementation of the function that we are trying to solve a problem by solving many smaller versions of the same problem. Okay, the implementation wise, we're actually the implementation of the function is calling the implementation of itself. But the implementation function may call a smaller version or smaller input for the same function. This sounds a little bit weird, right? How a function implementation can call itself. But think about this, functions are just the code. At the beginning of function is just the address. And calling that function is give the control flow back to the beginning of that function. So we actually can do this. So let's say we have a factorial function. One way to implement this factorial function is something like this. The input is long, the output is also long. We are trying to, the input is n here. We are trying to compute the factorial of the integer n here. Obviously, it's not a real number, it's an integer. So if n is 1, then its factorial is just 1, right? It's not supposed to be smaller than 1. It's not supposed to be. Yeah. But to make this code more complicated and more complete, we do check if it's smaller or greater. This is actually not a C symbol. C doesn't have this. In C, you have to write something like this, right? There's no such thing as this. Anyway, so this is my pseudocode. Okay. So if the input is 1, then this function will just return 1. If the input is not 1, then this function will compute n times the factorial of n minus 1. Okay. So look at here, fact. Okay. So this function, the implementation of this function is calling itself. It's calling itself. That's why this is called a recursive function. Okay, recursion. In C and other programming languages, you can do this. Here, originally, this fact function is trying to compute the factorial of n. But the implementation of this makes the problem, the input, a little bit smaller. We try to compute the factorial of n minus 1 first. Then we times that to n. Okay, so that's how we implement this. So how many of you heard about the Fibonacci numbers? Okay, so you can also use the same approach to compute the Fibonacci numbers of any number. Recursively, you add the two previous numbers together, right? It's not a very smart implementation. We're very slow. If you learn algorithm design, you learn something called dynamic programming, can make it much faster, but that can be implemented. So then how do we implement this in assembly? Let's see. Yeah, so this one. So the input here, this function, the input is only one parameter. You have a question? Yeah. Yes. There is a JE. Yes. So J basically means jump. Then there are different conditions. There is JLE, less and equal. JL, just for less. There is G for greater. There is for E great. JGE, right? For just for that, greater and equal to, or just JE equal to. And there are several others as well, because that is also related to those numbers are signed or unsigned. Yeah.
So does assembly not have a traditional system since the do while the while function performs itself?
So the do while, that's not a function. That's just one statement there.
Oh,
yeah.
Okay, but it's on stuff.
do while without putting any function.
Okay,
That's a safe statement.
okay,
Yeah, so the function here is that, the factorial, that's a function.
got it.
So let's say, maybe we should look at the complete version of this. Yeah, this is a complete version of this. Okay. This is a complete version of the assembly implementation of the factorial function, using the same algorithm. Okay, same algorithm as this piece of C code, which means this factorial function, that's the beginning of that. So at somewhere this function, we need to call that place. We need to go back to that place, right? So let's look for that first. Here, we have a call fact, okay? So in the implementation factor function, we have a call fact. So when we get here, we're going back to there. Okay. So the input of this function is an integer, and it's in the register RDI, right? Only first one parameter, so RDI. That's why we want to save the value n to a local variable in this case. So we move RDI to RBP minus 8. That's a local variable. And the local variable n here. So this is, so we're basically getting the n here. Then we compare if n is greater than 1. Okay. We're doing this compare. Here we're compare n is equal to 1, but here we compare if n is greater than 1. The same thing. So if it's greater than 1, we are going to this decrement thing here. We are going to, eventually we are going to call fact n minus 1. That's our goal, right? So how do we call n minus 1? Fact 1 minus 1. We need to set up the parameter for that. Parameter is still in RDI, and the parameter will be n minus 1 instead of n anymore, right? So what we're doing is first, this can be optimized a little bit. So what we're doing here is, this is n, okay? This is a local variable. We're moving this value to register RAX. Then we subtract 1 to RAX. So now we get n minus 1 in RAX. Then we move RAX to RDI. Okay. Why do we move to RDI? Because we need to pass the parameter. Then we make the function called fact. Okay. This can be optimized a little bit. At least these two can be optimized. Here we can directly move to RDI. Then we subtract RDI. Then we just make a call. We say one instruction there, right? We can do that. Yeah.
They didn't add comment inside RDI, so why didn't we like move it out? Like at the top in the body section, remove it to negative RDS.
That's a very good question. So here, first of all, you need to do a compare, right? When you do that compare, you can directly use RDI to do that. But later, you're going to come back to this function, and that n is still supposed to have the same value. If you use RDI, that will be tricky, because RDI value will be overwritten there, right? That's why we save that to a memory, to a stack place here first. Okay, but technically this compare here, you can still do RDI because they have the same value. Okay, but it's better to save it. There may be smart way to implement this that you can. For example, there are so many registers you can use here. You don't have to use a stack. You can use something like R13 or whatever to make this slightly faster, right? Yeah, that's possible. Yeah. So then here, you basically call fact n minus 1, and this call, when this call returns, which register will be changed? When this call function, this call instruction returns, which register will be changed? Which register will have the return value we want? Yes, right. So that's a convention. We always put a return value in RAX. So this call instruction doesn't explicitly tell you that the return value is in RAX, but you are supposed to put that there. So that's why the next instruction, what we're doing is we multiply n which we put on stack. Then we multiply that with RAX. So now you see why we're using stack here, we're not using a register here, because this can go very, very deep. If this is very deep, and if we put this N in a register, we'll run out of registers, right? That's why we use a stack address here. And this, for each invocation of this will be a different address. There are so many copies of it. And we have enough space on stack for this. So after that, we just leave and the beauty of this is the return address, the return value is always in RAX. That's also why we're putting RAX here. It's always there. Yeah. Then here we do not need to explicitly move it back to RAX. Yeah. Then we just leave and return. So let's take a look at a different, slightly, it's actually the same implementation, but I want to show you guys how it stack looks like. So we have main function. Main function takes two arguments. The first argument, system put it there. It's the name of the function, so you don't need to do anything. The second argument is a number. So basically, how to use this? You are going to do fact. That's the name of the function. So you put an integer there. That's it. Yeah. Put a command line integer. Then this one will just print out the string. The factorial of this number is then call this fact function. And this fact function is the same recursive function we saw just now, except we print out the address of N here. So N is a parameter. We print out the address. So let's say we have fact 5. We want to compute fact 5. So how does it work? So fact 5 will actually call function fact 4, which will call function fact 3, then call function fact 2, then call function fact 1. The function 1 returns 1, and the function 2 will times 2 with what function 1 returns. Then it will also return. The function 3 will 3 times what function 2. Back to 2 returns, right? So we go back. So if we run this on our platform, so what will the stack look like? Stack goes from high address to lower address, right? And the value will be getting smaller and smaller. We go to so this is a factorial function. This is directly compiled from the C code, not written in assembly, but very similar. We have a call here. We have a call here. This is a jump. This is a call. So this is a call to fact. So those two calls are called to printf. There is a printf. There's something else. What did we do there? Just the two printf. So those are the printf. So this is the fact function, and this is the instruction to call itself, right? This is the instruction call itself. It will multiply something here, ESP minus 20. So this one is also, this code you can see it's also somehow optimized. So it doesn't really use REBP in this piece of function. This code is not using EBP. It's only using ESP. Yeah. So saves, because this is a leaf instruction. This is a leaf function. That's interesting. Okay. Anyway, so anything after return, you don't need to care because they're basically garbage here because they're not going to be executed. Yeah. So let's run this. So if we do not give any command line arguments, it will just show us the usage. If we give a command line argument as to 5, it will give us output like this. Okay. So we first execute the function fact5, right? And we print out where n is, and it's at this address ffed ab d0. Okay. Then fact5 will call function fact4. Then print out the address of n again, and you can see n has a smaller address because fact5 is a caller, fact4 is a callee. The stack goes down. That's why the address is lower. Then fact4 calls fact3, fact3 calls fact2, fact2 calls fact1. Then fact1 returns, fact2 keeps executing by doing that multiplication. Fact2 returns, fact3 keeps executing, doing that multiplication. The fact4 return to fact4, return to fact5, eventually return to the main function, right? So this is how this is computed. So of course we can do a very big number for this, and oh, we crashed the program. The number is too big. Somehow we crashed the program. Yeah. So why do you think we crashed the program here? What was the number I gave? I gave a big number, right? This is a big number. We're computing the factorial of this number, okay, which will be a huge number. What will happen? Okay, so we got off of 5 to say that result. So basically, we were on the overflow something. Okay. So that overflow, let me look at source code. So this one is only 4 bytes. So definitely we're overflow. And when you overflow, we're doing this 50,000 times. It's also possible that because we do not have enough stack space for this program, I need to debug a little bit to figure out why exactly we crash the program. There are multiple reasons. Could be overflow somewhere here, and it also could be for each thread we have a pre-reserved number of space for its stack. Maybe this function is too deep, and then we used all the stack for that thread. Yeah, that's possible because we're basically calling this function 500,000 times, right? So are we doing 500,000 or? Oh yeah. No, we're doing 5 million times, right? So here is 7. This is 5 million. So we're calling this function 5 million times. So it's possible we use all the stack place. That's probably the crash. Yeah. More likely than flow there, actually. Cool. That's any questions so far? Okay. So you are able to finish assignment 2 now, I guess. Cool. So next week we are going to C programming. We're looking at some C syntax. You already see a lot of C syntax, but there are some weird ones that you only see in very complicated C project. But we're diving into OS later. That's a very complicated project. So we are going to look at some C syntax you do not necessarily already know. Okay. So after that, we read OS code. Okay. See you guys next week.